Not everything we see through our telescopes is just rock and ice. There are movements, tu deliberate, to be accidents, patterns in the light, numbers repeating, like a message waiting to be heard. October 21, a video appears out of nowhere. People claim it came from Japan's space agency. The object in the footage is labeled 3I Atlas, but what we see does not look natural. Not dust, not frozen rubble. It looks built, aligned metal plates, bright lines running along its body like power flowing through a machine. Listen carefully. If you want to follow every step of 3I Atlas from this moment forward, like this video, and subscribe. We are only beginning to uncover what the sky refuses to tell us. The footage is still a mystery. No verified source, no confirmation, but those few seconds changed everything. Because what is heading toward the sun may not be a comet. It may be a visitor. Dr. Avi Loeb, the controversial astrophysicist behind the Oumuamua hypothesis, has noted something unsettling. 3I Atlas is on an orbit that could allow a controlled maneuver, a solar slingshot, the kind of move an advanced probe would use to accelerate. Then came Tiago, un amateur astronomie in Brazil, known as Dobsonian power. He captured the object independently. Same coordinates, same intense bright head, and most importantly, no cometeu. Right now, it is racing toward the sun during a week when every telescope on Earth is blinded by sunlight. A strange time for a natural object, a perfect time for something else. Stay until the end. The next few days may bring answers to the oldest question our species has ever asked. Are we alone in the universe? If you're listening to this, take a moment. Look around you. Notice where you are and what time it is. Ask yourself whether the world is truly seeing the full truth of what is being discovered. If you feel the same, leave a comment. What do you think 3I Atlas really is? A strange comet or something looking back at us? I read every comment you write. Sometimes your question becomes the next chapter of this investigation. If you want the truth to spread, share this. You are the reason we can keep uncovering the stories that others are too afraid to touch. October 21. An object appears online that should not exist. The image shows something near the sun that looks nothing like a comet. It looks engineered. What you are seeing is blurry, compressed, and uncertain. A fragment of a clip passed from forum to forum through countless anonymous hands before it reached your screen. But what it shows is still too clear. An elongated shape, its surface reflective. It looks like metal, suspended in the blackness near our star. Along its spine, blue-white points of light glow in a perfect line, like running lights along the hull of a ship. No halo, no dust tail, no signs of evaporation. Only precision, only structure, a perfect axis of symmetry, motionless against the fire of the Sunday. Light radiating evenly from every surface. That object is 3I Atlas, the third interstellar visitor to ever enter our solar system. Discovered July 1, recorded first by the Atlas Telescope Network. A system designed to detect anything that could strike Earth. For 3 months, astronomers have been tracking it as it falls toward the Sunday. They have measured its trajectory, its changing brightness, its chemical signature. Everything points to a comet. A slightly unusual one, yes, but still a comet. A wandering block of ice, a visitor from a distant star, passing by without purpose. That was the story, until the image leaked, and everything we thought we understood began to break apart. A maneuver around the Sunday. The strongest gravity in the solar system. The great slingshot of space. We will come back to that. But first, we must trace the source of this footage, or at least get close enough to understand the intent behind it. We need to know who is speaking, why they spoke, and what they are not showing us. Because somewhere in that silence is the missing piece that keeps us from calling this real. Right now, we hold an image that could rewrite human history. And we do not know if it is authentic or a perfect lie. 3I Atlas is still out there, coming closer to the Sunday. The blind spot is open between the noise of scientific papers and unverified whispers. The truth is still waiting. The first clip appeared on X. Mid-morning ET, the 21st of October 2025. Users of varying credibility began sharing it, each adding a commentary, a speculation, a warning. The common thread: it came from Japan. Some mention JAXA, others university observatories, or the Sun Monitoring Network. But when you looked for an official statement, nothing. No press release, no internal warning, no observation logs, just silence. If you're listening and find this story worth following, give the video a like and subscribe to dive deeper into the next installment. We will need each other to keep this investigation going. The only consistent sign across every version is the watermark in the bottom corner. UFO 5537, a strange digital signature revealing nothing. A watermark can be added to anything, by anyone. It doesn't authenticate the content, it merely labels it. And in this case, the label feels intentionally vague, as if designed to provoke mystery rather than accountability. Ask yourself, if you were leaking top-secret data, would you stamp it with a code screaming, "Unidentified flying object"? Or would you wipe the metadata, anonymize the source, and distribute it through secure channels? This watermark feels performative, as if it wants to be noticed. That doesn't mean the footage is fake, but it does mean we must be careful. What's missing is everything that allows independent verification. Real astronomical data always comes with metadata. A technical fingerprint, a FITS file, contains every detail. Exposure time, filters, telescope coordinates, timestamps precise to the nanosecond, sensor temperature, and gain settings. If you hand an astronomer a raw frame, they can trace it back to the exact night, the exact telescope, the exact observing run. They can compare star positions, check whether the star field matches the claimed coordinates. They can examine the star's point spread pattern against the optical profile of the instrument. They can even verify the weather conditions, humidity, and seeing quality of that night. None of that is here. We only have a compressed clip, processed, filtered, stripped of every forensic detail that ties it to reality. In other words, we're left to guess. So why Japan? There are a few reasonable possibilities. Japan operates numerous advanced solar observatories run by national and university networks. The National Astronomical Observatory of Japan runs multiple high-cadence instruments observing the Sunday. Even JAXA maintains solar missions and ground support facilities. In theory, any of them could have pointed a telescope at the right coordinates, at the right moment, and recorded something unusual. But none of them have come forward. And that is the strangest part. If you owned the world's first discovery of its kind, you wouldn't stay silent. You would hold a press briefing. You would share the data, coordinate verification with other observatories. You would not leave a blurry, anonymous clip with a conspiracy bait watermark to flood the internet. A more plausible explanation. This is not official agency data. It could have come from a private observatory, an amateur network, or even a foreign intelligence asset. Conducting independent monitoring. Such scenarios are difficult to trace and even harder to verify. Private data has no accountability mechanism. You can't file a public request to someone's backyard telescope. And if the source is truly sensitive, if there is a reason they cannot reveal themselves, then we are stuck in the middle. There is evidence, but nothing we can authenticate. Then comes another question. Could the imagery be generated by artificial intelligence? The community has scrutinized every frame, searching for AI fingerprints. Some point to gradients that are too smooth, edges that are suspiciously sharp, and background blur almost too perfect. AI-generated visuals today are frighteningly realistic. Tools can create fake astronomical scenes with real-looking noise, star fields, and optical effects, indistinguishable from real instruments. If someone wanted to fake this, they absolutely could. But the counter-argument is compelling. Observations near the sun always require heavy filtering and aggressive processing. Sensor blooming, when a bright object saturates the detector, can produce halos that look fake. Compression algorithms smooth out details, making the image unrealistically clean. Looking too perfect doesn't automatically make it fake. It could simply be the result of intense processing to extract signal from noise. But the burden of proof rests on those making the extraordinary claim. And that claim is, this is an alien spacecraft. If you make that claim, you need more than a watermarked clip. You need instrument metadata, the original raw files. Independent confirmation from multiple observers in multiple locations using different equipment. You need emission spectra showing non-natural features. You need thermal signatures that don't match a comet. You need orbital data showing non-gravitational acceleration, something that can't be explained by sublimating ice. And until we have all of that, we only have one option. Keep observing, keep questioning, keep doubting. Extraordinary claims require extraordinary evidence. And right now, we don't have it. The timing makes everything more tense. 3I Atlas is about to slip behind the sun. From Earth's perspective, we are entering the solar conjunction window, a period where observational geometry makes detailed imaging nearly impossible. This is exactly when false positives become most common. Weak signals, heavy noise, solar glare, overwhelming the field of view. Instruments push to their limits to extract slivers of information from a blazing background. Under those conditions, technical illusions multiply. Diffraction spikes can look like structures. Internal reflections can mimic symmetry. Hot pixels can cluster into bright spots that look intentional. Astronomers know this well. They deal with it every night. And they enforce the strictest standards to separate real signals from the ghosts created by their instruments. So what do we have? From official channels, observations of 3I Atlas from Gemini, Hubble, the Very Large Telescope, and Keck in Japan, all show a comet. A dusty gas coma with slightly unusual chemistry, but nothing metallic. nothing spacecraft-like. Just a fuzzy cloud around a small, solid nucleus. The chemistry is strange. Yes, we'll get to that later. But the morphology is cometary. There is a faint tail. There are signs of gas jets. There are traces of sublimating ice under sunlight. Everything fits nature and nothing fits machinery. The media isn't helping. Click-driven headlines are exaggerating the mystery. They highlight the green glow. They inflate the nickel story. They tease metallic structures without explaining that natural processes can produce those effects too. We won't do that. We will separate fact from speculation so you can see the boundary clearly. So where are we now? The leaked footage is still unverified. It lacks metadata. It lacks independent confirmations necessary to call it genuine evidence. It appeared at exactly the time and under exactly the conditions when verification is hardest. The features that make it look artificial could just as well be artifacts of processing imagery. Near the Sunday, we don't know who created it. We don't know where it came from. We don't know if it's real, but we also cannot prove it's fake. We're trapped in an information fog. However, there is something else, another image. This one is verified, traceable, published by a known observer. An amateur astronomie using a solar telescope pointed to the exact coordinates at the exact time, capturing something that should not exist. If 3I Atlas is just a normal comet, that photo poured oxygen onto the leak. It doesn't prove the footage is real, but it keeps the door from slamming shut. And that alone is why this story refuses to die. Part 3. The difference between the leaked video and real comet observations. Look at what a real comet looks like when a serious instrument is pointed at it. A real comet is messy, diffuse, no sharp edges, no perfect symmetry. What you're seeing is just a solid nucleus, a few kilometers wide, surrounded by a diffuse coma, spreading tens of thousands of kilometers. Behind the nucleus, solar radiation pressure pushes dust outward, forming a tail, stretching millions of kilometers. Sometimes, there is even a second tail, an ionized plasma tail, glowing faint green in the dark. Those structures are shaped by the solar wind, by radiation pressure, and by the comet's rotation. They are dynamic, asymmetric, and constantly changing. 3I Atlas has been observed by the most powerful telescopes humanity has ever built. James Webb tracked it in infrared. Hubble captured optical and ultraviolet spectra. VLT and Kiki gathered high-resolution spectroscopy. All of them show the same thing: a comet, diffuse and hazy, with a coma, with signs of sublimation, with nothing suggesting a solid or mechanical structure. But the chemistry is strange, very strange. Astronomers detected cyanide gas, CN, in the coma of 3I Atlas. Cyanide is common in comets. It forms naturally in the cold, radiation-rich environments of interstellar space. Nothing unusual there. What is unusual is atomic nickel. Nickel vapor glows in the coma with an intensity far higher than what we expect from a comet inside the solar system. Even stranger, the spectral lines of iron, which normally accompany nickel when rocky material is vaporized, are weak or nearly absent. It's as if this comet is preferentially releasing nickel without iron. That makes no sense if you're simply heating up ordinary rock. There is a natural explanation, and it involves a bit of elegant chemistry. Under certain conditions, nickel can react with carbon monoxide to form nickel tetracarbonyl. This is a highly volatile compound, a gas, that can form at much lower temperatures than those required to vaporize pure metal. When sunlight strikes nickel tetracarbonyl, it breaks apart, releasing nickel atoms into the outflow, glowing at characteristic wavelengths that telescopes can detect. Iron cannot form a similar carbon compound under these conditions, so you see nickel but not iron. This process is unusual but not impossible. It's simply chemistry unfolding in an environment humans rarely get to observe directly. Spectrometers at KEK and the Very Large Telescope mapped the spatial distribution of CN and nickel around the nucleus. The signals concentrate near the core and spread outward in a pattern consistent with sublimation-driven jets. That is, the behavior of a comet. If this were a spacecraft, venting propellant or leaking coolant, you would expect narrow gas plumes, repeating pulses linked to attitude control, or concentrated thermal signatures at specific emission points. The spectral data shows none of that. It shows a solid nucleus losing material as it heats, exactly what a comet should do. Now, for the interesting part, there have been reports of a sunward tail, a jet of material pointing toward the Sunday. Most comet tails point away from the sun, pushed by radiation pressure. But occasionally, comets can show structures pointing inward. These are not true tails in the sense of dust reversing direction. They can be jets from the sun-facing side of the nucleus, or simply perspective effects when a curved dust trail is seen at a deceptive angle. Rare, but not without precedent. And for 3I Atlas, the appearance of a sunward feature coinciding with perihelion is an important detail. It indicates intense sublimation activity from the sun-facing side, exactly what you'd expect as a comet heats up. But the leaked footage tells a different story. The clip does not show a diffuse spreading coma. It shows an elongated object with sharp definition. The bright points along the body do not resemble diffuse gas. They look like discrete light sources, evenly spaced. The overall shape is rigid, structured, mechanical in appearance. No tail, no dust envelope, no chaotic jets. Just a clean cylinder, self-luminous, hanging in space. That is not what a comet looks like, even in extreme imaging conditions. Isolating a single spectral line, you still see diffusion, you still see soft edges, not sharp boundaries, with repeating geometric detail. The visual language is completely different. Yes, phase angle and filters can distort a comet's shape. Heavy image processing can produce geometric illusions. Nature can appear manufactured if you're not careful. But even accounting for all of that, the leaked clip remains difficult to reconcile with the morphology of 3I Atlas captured by the Major Telescope. NASA's official orbital data confirms the comet poses no threat to Earth. Its closest approach is about 1.8 AU, roughly 168 million kilometers, nearly twice the Earth-Sun distance. If the clip makes the object appear close to Earth, that is an illusion of perspective and framing. It is not coming toward us. It is plunging toward the sun, and after perihelion, it will arc back out of the solar system, never to return. The flight path geometry is confirmed by months of observations. No ambiguity about its destination. Only one question remains. What is it, really? Sensational headlines have only made things noisier. The green glow from CN is entirely normal. Metal alloy emissions are just a misunderstanding between atomic nickel and metallurgy. These distortions feed narratives that don't fit the scientific record. We will stick to vetted data. If the data changes, we will update. As of now, strange chemistry, but a shape inconsistent with a spacecraft, except for the leaked image. And that image doesn't align. It shows something not comet-like in any scientific observation. It looks engineered. That discrepancy is exactly what turned it into the center of the debate. The thing no one can look away from. There is one motipiece, an orbital trick that only intentional intelligence would know to exploit. The Oberth effect. Understand that, and you will understand why disappearing behind the sun matters so much. Because if you want maximum acceleration to leave a star system, there is only one place to fire your engines, and that is exactly where 3I Atlas will be 9 days from now. The telescope image, taken by Thiago, also known as Dobsonian power, on October 20th, 2025, on Amateur Astronomie, named Thiago, posted a raw frame from his solar telescope. Online, he goes by the nickname Dobsonian Power, a name that reflects his passion for large aperture telescopes, manually operated, often used for deep sky observing. But Thiago also maintains a setup for solar imaging, and that morning, he pointed his telescope at a specific set of coordinates derived from NASA's ephemeris data for 3I Atlas. He captured something. The image shows a concentrated, bright region standing out against the diffuse glow of the solar corona. There is a clearly defined forward-facing structure, a shield, as some observers described it, tilted toward the Sunday. Behind this bright front is a fainter, uneven plume of material, cone-shaped, less luminous than the leading section. What matters is there is no long tail, no stream of dust trailing away from the Sunday, just a concentrated structure at the front with a short, faint plume behind it. This is verified data in the sense that Thiago is a known observer with a clear public track record. His post includes coordinates, timestamps, and equipment details. Other amateur astronomers have cross-checked his pointing direction, with JPL ephemeris data confirming that he was indeed observing the correct location at the correct time. This is not an anonymous leak. This is community-level verification, traceable and accountable. It isn't agency-certified science or peer-reviewed data, but it's also not worthless. It is a data point. The raw frame is covered with color noise, hot pixels, dead pixels, and sensor artifacts, amplified by high sensitivity and the sun's harsh light. This is completely normal when imaging near the Sunday. Trying to capture a faint object next to the sun's brightness pushes the detector to its limits. You increase exposure as much as possible without saturating the solar disk. You raise sensitivity to pull any signal from the blazing background. And when you do that, every flaw in the sensor becomes obvious. The result is a noisy frame that demands careful processing. To extract meaningful signal, Tiago posted the raw data, exactly what you want to see. Raw means untampered. It allows others to independently verify, evaluate noise behavior, and determine whether the structures we see are real or digital ghosts. This frame confirms there is something at the predicted coordinates, at the predicted time. Its morphology does not fit a typical cometary coma, nor does it resemble a star or a background galaxy. The brightness concentrated at the front is striking. Most comets brighten more uniformly or show jets emerging in multiple directions. A strong forward-facing, asymmetric bright region is unusual. It could be a sunward jet, material escaping from the hemisphere, facing away from the sun. As that surface heats up, that aligns with reports of a sunward tail from spectroscopic observations. The sun-facing side could be highly active, venting gas and dust directly toward the star, producing a compact, bright feature with no time to diffuse before the observer's line of sight cuts through it. Or it could be something else, forward scattering. When sunlight hits tiny particles, it scatters in all directions. But one scattering angle is favored, boosting brightness when you view the object from a specific geometry. If 3I Atlas has a dust cloud concentrated on its sun-facing side, and Tiago's viewing angle happened to align with that favorable scattering zone, you would see exactly this kind of strong forward brightness. That is an optical effect, not a physical structure. Brightness is not the object's intrinsic property. It is the result of sunlight interacting with dust at that phase angle. This effect is well understood in planetary science. It's why the moon appears brighter when full than when crescent. It's why Saturn's rings blaze when Earth crosses the ring plane. Physics, not propulsion. But then there is the cone, a faint, diffuse structure trailing behind the bright front. If this were just forward scattering, brightness would fade smoothly with distance from the nucleus. Instead, there is a defined conical shape, like a jet or a directed plume, suggesting material escaping in a preferred direction. Comets do this often. They develop jets that create asymmetric comae and strange tail structures. What stands out here is the absence of a long tail. At the current distance between 3I Atlas and the Sun, solar radiation pressure should already be pushing dust into a clear tail. The fact that Tiago's image doesn't show such a tail could mean a lower than expected dust production rate, or a grain size distribution skewed toward larger particles that are harder to push away. Or something in the observing geometry is obscuring the tail. Or, if we consider an alternative hypothesis, there is no tail because this isn't a comet venting dust. It is a vehicle venting something for thermal management or for thrust. And whatever it is venting doesn't behave like cometary dust. The chemical data supports unusual activity on the sun-facing side. The detection of CN and nickel in the coma, combined with the spatial distribution, shows a concentration near the nucleus, consistent with the idea that the sun-facing hemisphere is highly active, sublimating volatiles. The carbonyl chemistry pathway we discussed earlier may be operating at peak efficiency on that side, releasing nickel atoms. As the surface heats up, this can produce a localized bright region without any artificial process. It is strange, but it can be natural. Tiago's image must be carefully evaluated for possible artifacts. Solar telescopes contend with atmospheric turbulence and heat ripples that can distort structure. The sun heats the ground, creating convection cells in the air above the telescope. Those cells act like shifting lenses, bending light and blurring the image. High-speed imaging and lucky imaging techniques can reduce this effect, but image distortions never fully disappear. You can capture false structures. You can see symmetry that is only an illusion. The fact that multiple observers, including the one who posted the leaked clip, report similar morphology helps rule out a single-frame artifact. If only one person saw it, it could be dismissed as a sensor error. But when multiple independent sources describe consistent features, it becomes harder to ignore. What this frame does not do is prove that 3I Atlas is artificial. It only demonstrates that something unusual in shape is present at those coordinates. It confirms that the object's morphology is strange enough to warrant closer study. It validates that the leaked clip, whatever its origin, is at least depicting a real object existing at that location. It doesn't tell us what the object is. It only tells us that it is there and that it looks strange. NASA's distance and orbital data remains the anchor. The object is not approaching Earth. It is not on a collision trajectory. The story around 3I Atlas is not about existential danger. It is about the possibility, however small, that we are witnessing a phenomenon that does not fit our standard model of comet behavior. What sharpens the speculation is the timing. The moment this object approaches the optimal position for a high-energy maneuver. If you wanted to accelerate a spacecraft using the sun's gravity, you would do it at perihelion. You fire the engines at the lowest point of the orbit when you are moving fastest and the gravity well is steepest. Every bit of velocity added at that moment is multiplied by the depth of the gravitational well. That is the Oberth effect. And it is one of the most efficient techniques in orbital mechanics. 3I Atlas will pass through that exact sweet spot in 9 days, while telescopes on Earth remain blinded. By the Sunday, the Oberth effect isn't science fiction. It's orbital mechanics, basic physics any spacecraft engineer learns in the first semester. The principle is simple. If you want to change energy in an orbit, you do it when you're moving fastest. When you fire the engine, the energy you add to the spacecraft depends not only on thrust, but also on your velocity at the moment of ignition. The faster you go, the more kinetic energy each unit of fuel contributes to your total. It sounds counterintuitive, but it's perfectly correct mathematically. Firing at the bottom of the gravity well, where orbital velocity is highest, delivers maximum effect compared to firing in deep space, where you're moving more slowly. Human missions have used this principle for decades. Voyager flew past Jupiter and Saturn using gravity assists to steal a bit of momentum and exit the solar system. Cassini looped multiple times to reshape its trajectory and enter the Saturn system. Galileo swung by Venus and Earth to gain enough energy to reach Jupiter. Every deep space mission accounts for the Oberth effect. It's how we go far without carrying absurd amounts of fuel. Now apply that logic to an interstellar probe. If we consider the alternative hypothesis that the absence of a tail means this is not a comet releasing dust, but a vehicle venting something for thermal regulation or propulsion, then whatever it is releasing might not behave like ordinary cometary dust. The chemical data also seems to support this possibility because the strong signals on the sun-facing side indicate unusual activity is occurring there. The detection of cyanide and nickel in the coma, combined with their spatial concentration near the nucleus, is consistent with the idea that the sun-facing hemisphere is highly active, sublimating volatile compounds as it heats up. The carbonyl chemistry pathway we discussed earlier may be operating at maximum efficiency on that side of the surface, releasing nickel atoms as the temperature rises, creating a localized bright region without requiring any artificial mechanism. This phenomenon is strange, but not impossible in nature. Thiago's image must be carefully evaluated because solar telescopes face harsh observational conditions, atmospheric turbulence, heat ripples, and optical distortions that can warp true structure. When the sun heats the ground, convection cells form in the air above the telescope, acting as shifting lenses, bending light and blurring the image. High-speed techniques and lucky imaging can reduce these distortions, but artifacts never fully disappear. You can record false structures, symmetries that are nothing more than products of the atmosphere or the sensor. Yet when multiple observers, including the one who released the leaked clip, report similar morphology, that possibility becomes harder to dismiss. If only one person observed this shape, it could be rejected as sensor noise or error. But when several independent sources capture consistent features at the same time and coordinates, we are forced to seriously consider that the morphology is real. What this frame cannot do is prove that 3I Atlas is artificial. It only shows that something real exists at that position, an object with an unusual shape, an optical signal worthy of further analysis. This image validates that the leaked clip, whatever its origin, is at least depicting a real object located there, even if it doesn't tell us what the object actually is. It only shows that something exists and that it appears unusual. According to NASA's published orbital distance data, the object is not approaching Earth, and it is not on any collision trajectory. The story of 3I Atlas is not about danger, but about the possibility, however small, that we are witnessing behavior that does not fit the standard comet model. The timing of the phenomenon is what sharpens every hypothesis. As the object approaches perihelion, it is entering the ideal position for a high-energy maneuver. If you wanted to accelerate a spacecraft using the sun's gravity, that is exactly where you would do it. At perihelion, the spacecraft is moving fastest, and the gravitational gradient is steepest. Every unit of velocity added there is multiplied by the depth of the gravity well. This is the Oberth effect, one of the most efficient principles of orbital mechanics ever used by humans. According to calculations, 3I Atlas will pass through the optimal position for the Oberth effect in 9 days, at the exact moment when every telescope on Earth will be blinded by the Sunday. The Oberth effect is not mysterious. It is basic physics, a principle every aerospace engineer learns in their very first semester. If you want to change orbital energy, you do it when you are moving the fastest. When you fire your engines, the energy you add doesn't only come from thrust, it also depends on your velocity. At the moment of ignition, the faster you are going, the more kinetic energy each unit of fuel contributes. It sounds paradoxical, but it is mathematically precise. Firing at the bottom of the gravity well, where orbital velocity peaks, multiplies the effect, compared to burning fuel in deep space, where you are moving more slowly. Human space missions have used this principle for decades. Voyager flew past Jupiter and Saturn, using gravity assists to steal a bit of momentum and hurl itself out of the solar system. Cassini used repeated flybys to reshape its trajectory, inserting the spacecraft into Saturn's system. Galileo swung by Venus and Earth to pick up enough energy to reach Jupiter. Every deep space mission accounts for the Oberth effect. It is the only practical way to go far without carrying absurd amounts of fuel. And if you apply that logic to an interstellar probe, the position hidden behind the sun is the perfect ignition point. An Oberth burn to accelerate away from the solar system is the most fuel-efficient way to depart. You would fire your engines right at perihelion, When the object is moving fastest relative to the Sunday, each kilogram of fuel burned at that moment adds more total energy than at any other time. You leave faster and farther for less propellant than any alternative. The second branch of this strategy is more unsettling. If the object fires its engine in the retrograde direction, it can reduce velocity, slow down, and instead of escaping the solar system, it can fall into a bound orbit. In that case, the object stays. It lingers within the inner planetary region, continuing observations, deploying smaller devices, or establishing some form of infrastructure. A deceleration burn at perihelion is still highly effective because it is performed at the highest speed, but the outcome is reversed. Instead of leaving, the object captures itself into a new orbit. It anchors. It establishes a foothold. Both scenarios are speculative. Both require evidence we do not currently possess. Yet both fit the Oberth maneuver as a propulsion strategy, and both explain why the sun hidden phase is so critical. If you plan to fire engines, you do it when no one can see. You choose a moment when the sun's glare can hide your exhaust plumes. You choose when every Earth telescope is blinded and the only witnesses left are spacecraft not designed to watch you. Now let's connect this to the leaked footage. If those evenly spaced bright nodes along the spine of the object are real, what could they be? One interpretation is that they are clusters of thrusters, arranged along a central frame to provide attitude control and maneuvering capability. Another interpretation is that they are heat radiators. Any propulsion system generates heat, and if you are performing a high-energy burn near the sun, you must have a way to dump excess heat or the entire system will overheat. Such radiators could glow intensely, emitting infrared and sometimes even visible light if they become hot enough. A spacecraft with an active thermal management system could produce exactly the kind of evenly spaced bright nodes people are seeing in the leaked clip. Or they could simply be sensor artifacts, diffraction spikes, internal reflections inside the optical tube, CCD saturation around a concentrated bright core, hot pixels clustering into a pattern that appears intentional but isn't. The key lies in the post-perihelion data. When 3I Atlas emerges from solar conjunction in early November, observers across the world will swing their telescopes toward it. They will measure its position, its velocity, and its spectrum. They will compare the observed trajectory with the predicted gravity-only orbit. If there is a discrepancy, if the object gains or loses velocity in a way that cannot be explained by natural cometary outgassing, the hypothesis of an artificial burn becomes more credible. If the orbit does not change, if its position matches Newtonian predictions perfectly, that hypothesis collapses. We will know, but not immediately. It will take time to gather enough data, enough precise position measurements, to detect subtle deviations. Within a few weeks, orbital analysis teams will have the answer, and during that time, we remain in the dark, literally. The sun stands between us and the object. We cannot see anything. The blackout window is open. If something is happening, it is happening right now, and we will not know until it's already over. This is the core of the Oberth narrative. It is not meant to prove that 3I Atlas is artificial. It is a lesson in what a mission profile would look like if it were artificial. This is when you would fire the engines. This is when you would hide that burn. And the fact that amateur observers have captured strange images right before the object disappears from view is exactly what keeps everyone staring. Unusual morphology, convenient timing, strange chemistry, a reasonable orbit. None of this proves intent, but all of it raises the question. And in the coming weeks, we will have the data to answer some of those questions, or perhaps only to create more. Either way, the next act of this story is about to begin, and all we can do is wait. As the object sweeps behind the sun, as the telescopes on Earth go blind, as the blackout window closes and then opens again on the far side, we can only trust that the data will arrive and prepare for what it might reveal. The human brain is an extraordinary pattern recognition machine. It evolved to detect predators in the dark, to see faces in clouds, to find order in chaos. Because in the primitive world, order often meant intention, and intention meant either danger or opportunity. That is why we see animals in clouds, faces on rock formations, and perhaps a spacecraft in the image of a comet. We are wired to interpret ambiguous visual data as meaningful structure. The question is, are the features we see in the images of 3I Atlas real patterns or just pareidolia? Is there truly something that does not fit nature? Or are we simply doing what humans always do? Seeing what we want to see? Looking closely at the leaked image, the object appears elongated like a spindle, its length many times greater than its width. It is not spherical, not an irregular chunk of rock. It is a long bar with distinct bright points along its central axis. Not continuous light, not random scattering, but evenly spaced luminous nodes, each with similar brightness and color. Their spacing seems arranged with deliberate geometric proportion. Connect them, and you trace a straight spine with equal intervals. Such regular repetition is rare in nature. Crystals can be symmetric at the microscopic scale, but on the macroscopic scale, objects formed from ice and rock rarely arrange themselves into evenly spaced luminous patterns like this. Then there is the blue-white glow surrounding the entire object, creating a smooth halo effect, enhancing the sense of symmetry and making it appear as though it is shining from within. The brightness is almost constant from end to end. There is no defined nucleus, no single bright core like a normal comet. Only a uniform, smooth light, making it look as if it is generating its own energy, rather than simply reflecting sunlight. If you had to design a spacecraft for interstellar travel, it might look very much like this. The answer would depend on your engineering limits, and the biggest limit is speed. If you travel at a significant fraction of the speed of light, you need a shield at the front to absorb interstellar dust and gas. A Whipple shield, named after astronomer Fred Whipple, is a layered impact mitigation system designed to vaporize incoming particles before they can strike the critical parts of a spacecraft. You would place that shield at the nose, at the very front, facing the direction of travel. It becomes the protective plate, reflecting and vaporizing anything approaching head-on. If sunlight strikes it at the right angle, it will blaze like a metallic mirror hanging in the black. Behind that shield is the spine, a structural backbone running the length of the craft, connecting propulsion systems at one end with habitat and sensor modules at the other. Along that spine, you might mount everything needed for motion and survival: fuel tanks, power units, radiators, communications arrays, navigation controls, attitude control systems. Each one of those components carries its own optical signature, a trace of heat, a vibration, a whisper of electromagnetism detectable by telescopes sensitive enough, especially the radiators. If the power system is running hot, if there is a high-energy maneuver underway, those radiators will glow. They emit strongly in infrared, and if the heat is intense enough, that light overflows into the visible range. From a distance, a spacecraft with active thermal regulation would appear as a long metallic rod with evenly spaced bright spots along its body, exactly what people report seeing in the leaked footage. Another possibility: attitude, control thrusters, small engines used to maintain heading, to keep the craft from tumbling, to adjust orientation 1 degree at a time. They are positioned around the center of mass, firing in sequence, creating short, regular bursts of light. If someone captured a long exposure image while the craft was performing such a maneuver, those discrete bursts would overlap into a chain of evenly spaced bright nodes. And as every engineer knows, symmetry is preferred. Symmetry keeps balance, and balance keeps control manageable, but it may all be natural. Could a comet produce a shape like this? Yes, it is possible. Rare, but possible. 1. Oumuamua had a length-to-width ratio of about 10:1, a cigar-shaped shard of rock tumbling through interstellar darkness. If 3I Atlas is similarly elongated, and if our viewing angle happens to align closely with its rotation axis, it would appear as a narrow bar, slowly spinning. The question is whether that interpretation matches the photometric and spectroscopic data collected by telescopes, data that still indicates typical comet-like behavior. And those bright nodes? They could be jets viewed head-on. Comets develop active regions as sunlight heats their surface, turning ice into gas and blasting jets of dust into space. If 3I Atlas has multiple active patches and we are looking nearly along the direction of a jet, each region could appear as a distinct bright spot. The spacing between these spots depends on geometry and rotation, often random but sometimes repeating if the nucleus has structural regularity, like cracks or compositional boundaries. Difficult but not impossible. Another possibility is forward scattering. Sunlight striking tiny particles is preferentially scattered in the direction of motion. If 3I Atlas has a dust cloud concentrated around the nucleus and our viewing angle aligns with that direction, the entire front region would brighten. But this scattering tends to create smooth, soft light, not distinctly separated points. To get discrete nodes, you would need dense clumps of dust released intermittently in pulsed jets. Each pulse would form a slightly brighter region, and if the process repeats regularly, it could appear like engineered lighting. However, in nature, such regularity doesn't last. Dust clumps disperse, fade, and the spacing shifts. The fact that multiple images show the same bright positions weakens this natural explanation. Another possibility is image processing error. In astronomy, when you try to enhance detail, you use deconvolution techniques to undo the blurring of the optical system, but that also amplifies noise. Push it too far, and false structures can appear around bright regions. Glowing specks, symmetrical lines that look organized but are only illusion. Professional astronomers always compare processed frames to the raw data to avoid that, which is why Tiago's original frame matters so much. He didn't overprocess it, and the forward-facing bright region still appears. So either many independent processing tools all coincidentally produce the same error, unlikely, or there really is a structure there. And then there's the strange chemistry. Nickel and cyanide, two elements that seem unrelated, yet are linked by the carbonyl pathway. Carbonyl chemistry can explain why atomic nickel appears without iron, but it requires special conditions: low temperatures, stable pressures, and enough sunlight to break the compound apart. If that process is occurring around 3I Atlas, it implies strong thermochemical activity near the nucleus. Nickel tetracarbonyl forms. Sunlight breaks it apart, releasing nickel atoms that emit light at detectable wavelengths. If this emission is concentrated in certain regions due to uneven temperature or material distribution, it will produce distinct bright points. That is a natural reaction, but also exactly what would happen if a spacecraft were venting hot nickel gas from its propulsion or cooling system. Finally, perspective and filters. If you observe 3I atlas through a CN filter, you are only seeing gas, not dust. The coma will shrink, sharpen, brighten, and active regions will stand out clearly. Switch to infrared and you see heat, soft glowing streaks of warm dust drifting away. The shape of 3I atlas changes completely. If you observe it in visible light without a filter, you will see sunlight reflected from the nucleus and dust, plus luminescence from gas. The object looks diffuse and hazy. Some leaked images are in blue or white light. This emphasizes symmetry and the smoothness of the surrounding layer. Tiago's frame may have used a solar observing filter. It blocks certain wavelengths so that the sensor does not saturate. Each filter tells a different story. The task is to figure out which story is correct. Phase angle is also important. The phase angle is the angle between the sun, the object, and the observer. At certain phase angles, small dust grains flare opposite the sunday. Light is reflected directly toward the observer. The object appears unusually bright. This can make a dust coma look like a shiny metallic surface. Conversely, at another angle, the same particles darken. If 3I atlas is at a phase angle where forward scattering is strong or flaring is pronounced in the anti-sun direction, natural materials can mimic reflective metal. This effect is well documented in planetary science. Icy moons, dust rings, even the lunar surface all show phase-dependent brightness. They can easily be mistaken for intrinsic material properties. The rotation state of 3I atlas can be verified. If the object tumbles, the bright nodes move in and out of view. Their positions shift over time, following a predictable pattern linked to the rotation cycle. If the nodes are fixed on the surface, they move with the surface. If the nodes are telescope or processing artifacts, they do not move. If they are radiators or thrusters fixed on a spacecraft, they also remain stationary. But for another reason, high-speed imaging distinguishes the cases. Continuous observation over several hours, tracking the nodes, seeing if they rotate. A similar situation occurred with Oumuamua. It was elongated. It tumbled. Its acceleration could not be explained by gravity alone. For 2 years, scientists debated. Was it a comet with asymmetric outgassing or something else? Some proposed it was a chunk of hydrogen ice. Others suggested a fragment of a destroyed extrasolar planet. A paper by Avi Loeb and a graduate student proposed the possibility of a light sail, a thin reflective membrane. Pushed by starlight, the paper caused a storm, not because it was irrational, but because it crossed boundaries. It considered an artificial origin. There was no extraordinary evidence. The scientific community reacted strongly. In the end, the consensus leaned toward a peculiar comet with low outgassing. Most researchers moved on to other topics, but the debate showed that shape can deceive us. Being elongated does not mean it is artificial. Unusual acceleration does not mean there is propulsion. Still, the question remains. We do not yet have a complete natural explanation for all observations of one eye. A plausible explanation exists, but nothing is definitive. Now we look at 3I atlas. The questions return, bigger than before. The path forward is high cadence, multi-wavelength imaging. Observe the object through multiple filters simultaneously. Track the brightness and color of each node over time. Look for rotation. Look for light variations. Look for spectral lines matching known molecules, or emission consistent with artificial illumination. Compare the point spread function, PSF, of the nodes with nearby stars. If the nodes are real physical features, the PSF will match. If they are artifacts, the PSF will be distorted. This is forensic astronomy. The images are the crime scene. Remaining evidence helps reconstruct the story. If the evidence shows the nodes are real, not rotating, emitting light, inconsistent with cometary chemistry, we have a problem. 3IATLAS is not a comet. We are observing an unnatural object, never seen before. First, we need to consider timing. Unusual morphology is only part of the story. Orbit is the rest. Look at where 3I Atlas is headed, how it moves through the solar system, where it will go. The coincidences begin to emerge. Interstellar space is unimaginably vast. The nearest star system, Alpha Centauri, is 4.3 light-years away, about 25 trillion miles. Choose a random direction in the sky, throw a rock. The chance of hitting the solar system is nearly zero. Space is mostly empty. Stars are tiny targets, separated by a void. For an object to reach the sun from interstellar space, it must be targeted, or deflected by gravity, perturbed by galactic potentials, encountering stars over millions of years, then by chance cross our system, or it is intentionally aimed, launched on a trajectory designed to arrive. Interstellar objects arrive from random directions. A three-dimensional galaxy, no preferred orientation. The Milky Way plane is flat on a galactic scale, but the scale of individual star systems does not require alignment with anything specific. An object could come from above or below the ecliptic plane. The ecliptic plane is where Earth and the planets orbit the Sunday. It is defined by the angular momentum of the protoplanetary cloud that formed the planets 4.6 billion years ago. This is the local plane of our system. An interstellar visitor does not care about it. Yet 3I Atlas approached from roughly 5 degrees relative to the ecliptic plane. 5 degrees is close, not perfectly aligned, but close enough that if you were surveying planets in the system, you would aim at that configuration. The shape of 3I Atlas changes completely. If you photograph it in visible light without a filter, you see sunlight reflected from the nucleus and dust, plus luminescence from gas. The object looks diffuse and hazy. Some leaked images are in blue or white light. This emphasizes symmetry and the smoothness of the surrounding layer. Thiago's frame may have used a solar observing filter. It blocks certain wavelengths so that the sensor does not saturate. Each filter tells a different story. The task is to determine which story is correct. Phase angle is also important. The phase angle is the angle between the sun, the object, and the observer. At certain phase angles, small dust grains flare opposite the Sunday. Light is reflected directly toward the observer. The object appears unusually bright. This can make a dust coma look like a shiny metallic surface. Conversely, at another angle, the same particles darken. If 3I Atlas is at a phase angle with strong forward scattering or strong anti-sun flaring, natural materials can mimic reflective metal. This effect is documented in planetary science. Icy moons, those rings, even the lunar surface, all show phase-dependent brightness. They can be mistaken for intrinsic material properties. The rotation state of 3I Atlas can be verified. If the object tumbles, the bright nodes move in and out of view. Their positions shift over time, following a predictable pattern linked to the rotation cycle. If the nodes are fixed on the surface, they move with the surface. If the nodes are telescope or processing artifacts, they do not move. If they are radiators or thrusters fixed on a spacecraft, they also remain stationary. But for another reason, high-speed imaging distinguishes the cases. Continuous observation over several hours. Track the nodes, see if they rotate. A similar case occurred with Oumuamua. It was elongated. It tumbled. Its acceleration could not be explained by gravity alone. For 2 years, scientists debated, was it a comet with asymmetric outgassing Or something else? Some proposed it was a chunk of hydrogen ice. Others suggested it was a fragment of a destroyed extrasolar planet. A paper by Avi Loeb and a graduate student proposed the possibility of a light sail, a thin reflective membrane pushed by starlight. The paper caused a storm, not because it was irrational, but because it crossed boundaries. It considered an artificial origin. There was no extraordinary evidence. The scientific community reacted strongly. In the end, the consensus leaned toward a peculiar comet with low outgassing. Most researchers moved on to other topics, but the debate showed that shape can deceive us. Being elongated does not mean it is artificial. Unusual acceleration does not mean there is propulsion. Still, the question remains. We do not yet have a complete natural explanation for all observations of one eye. A plausible explanation exists, but nothing is definitive. Now we look at 3I Atlas. The questions return, bigger than before. The path forward is high cadence, multi-wavelength imaging. Observe the object through multiple filters simultaneously. Track the brightness and color of each node over time. Look for rotation. Look for light variations. Look for spectral lines matching known molecules, or emission consistent with artificial illumination. Compare the point spread function, PSF, of the nodes with nearby stars. If the nodes are real physical features, the PSF will match. If they are artifacts, the PSF will be distorted. This is forensic astronomy. The images are the crime scene. Remaining evidence helps reconstruct the story. If the evidence shows the nodes are real, not rotating, emitting light inconsistent with cometary chemistry, we have a problem. 3I Atlas is not a comet. We are observing an unnatural object, never seen before. First, we need to consider timing. Unusual morphology is only part of the story. Orbit is the rest. Look at where 3I Atlas came from, how it moves through the solar system, where it will go. The coincidences begin to appear. Interstellar space is unimaginably vast. The nearest star system, Alpha Centauri, is 4.3 light-years away, about 25 trillion miles. Pick a random direction in the sky. Throw a rock. The chance of hitting the solar system is nearly zero. Space is mostly empty. Stars are tiny targets, separated by a void. For an object to reach the sun from interstellar space, it must be targeted or deflected by gravity, perturbed by galactic potentials, encountering stars over millions of years, then by chance cross our system, or it is intentionally aimed, launched on a trajectory designed to arrive. Interstellar objects arrive from random directions, a three-dimensional galaxy. No preferred orientation. The Milky Way plane is flat on a galactic scale, but individual star systems do not need to align with anything. An object can come from above or below the ecliptic plane. The ecliptic plane is where Earth and the planets orbit the Sunday. It is defined by the angular momentum of the protoplanetary cloud that formed the planets 4.6 billion years ago. This is the local plane of our system. An interstellar visitor does not care about it. Yet 3I Atlas approach from roughly 5 degrees relative to the ecliptic. 5 degrees is close, not perfectly aligned, but close enough that if you were surveying planets in the system, you would aim at that configuration. All planets orbit the Sunday. They lie within a few degrees of the ecliptic. If your goal is to fly past multiple planets in a single pass, you launch on a trajectory that intersects the ecliptic plane at a shallow angle. That way, you maximize the chance of encountering planets. No large course corrections required. That is mission design 101. Efficient. Taking opportunities. Exactly what you do when fuel is limited, and you want to observe as much as possible. The orbit of 3I Atlas brought it near Venus, Mars, and Jupiter, not close enough to collide, but within tens of millions of miles. With Venus and Mars, it was a close approach. By interstellar standards, with Jupiter, it was a more distant pass, but still within the planet's gravitational influence. If you were a reconnaissance probe, these are priority targets. Venus to study a runaway greenhouse atmosphere. Mars to check for extinct or surviving life. Jupiter to sample its magnetosphere and to observe the Galilean moons. 3i Atlas's trajectory intersects all of those targets. One could argue this is selection bias. We only notice interstellar objects that come close to the Sun because those are the objects we can detect. Objects passing through the outer solar system, never approaching the inner regions, are too faint for our surveys. So each year, there may be hundreds of interstellar visitors, but we only see those that happen to come close enough and at the right viewing angle to be detected. That makes sense. Detection efficiency favors objects approaching the Sunday. They brighten due to solar heating. But even accounting for that bias, the alignment with the ecliptic plane remains unusual. There are many possible trajectories that bring an object close to the Sunday. Most are not aligned with the ecliptic plane. The alignment of 3i Atlas is a statistical outlier, not impossible, just unlikely. Its distance and the timing of perihelion increase the peculiarity. Perihelion occurs around October 29 or 30, 2025. Distance approximately 1.36 to 1, 4 AU from the Sunday. That is inside Earth's orbit, but outside Venus' orbit. This point is favorable, close enough to the Sun to heat volatile ices, making the comet brighten strongly, but not so close that structural damage occurs from thermal stress. If you perform a high-energy maneuver, you want to approach the Sun as closely as possible without overheating the spacecraft. 1.4 AU is reasonable for that. Hot, but manageable with proper heat shielding. The closest approach to Earth is about 1.8 AU, approximately 168 million miles, farther than the Sun, so there is no risk of collision or close flyby. The geometry places Earth to the side, while 3i Atlas heads toward the Sunday. But from Earth's viewpoint, the object and the Sun appear nearly aligned in the sky. This is the solar conjunction. The Sun's glare overwhelms any nearby faint objects. That is why we cannot observe Mercury and Venus when they pass behind the Sun from Earth's perspective. The Sun is too bright. Contrast is too high. Telescopes and cameras cannot separate a faint object from the overwhelming background. Solar conjunctions happen frequently in spaceflight. When a spacecraft traveling to Mars or Jupiter passes behind the Sun from Earth's perspective, we lose contact for days or even weeks. NASA's Deep Space Network does not maintain radio communication because the Sun's radio emission overwhelms the spacecraft signal, and the solar plasma distorts transmissions. Mission planners design around this. They preload command sequences, put the spacecraft into safe mode, wait for the end of the occultation period, then resume operation. This is a known operational limit, and it is perfect shielding for any maneuver you do not want observed. If 3i Atlas is a spacecraft and it intends to perform an Oberth burn at perihelion, the occultation window provides natural operational security. Telescopes on Earth cannot see you. Earth-based radar cannot track you. Radio observatories cannot detect your signals because solar radio emission is too strong at those frequencies. You are hidden, but not invisible to other spacecraft in the solar system. SOHO, stereo, some planetary orbiters. They might catch it depending on viewing geometry. But those platforms are not optimal, not optimized for high-resolution imaging. Faint objects move fast. Their main mission is to observe the Sun or planetary science, not to track comets. The chance of capturing a transient engine burn is low unless someone is specifically looking for it. Then there is the anti-sun tail. Many spectroscopic observations reported a jet or an extension of the coma pointing toward the Sunday. A reverse tail is rare in comets. Normally, radiation pressure pushes dust away from the sun, creating sunward tails. A sunward feature suggests outgassing is active from the sun-facing hemisphere. That makes sense because it is the hottest side, or it could be a viewing angle effect when a curved dust streak appears misaligned. But geometric effects are usually fleeting. Features change as viewing geometry changes. If the sunward feature persists over multiple observations at different days and angles, it is likely a real physical structure, a jet material flowing from the nucleus toward the Sunday. Why would a comet do that? Sublimation jets usually follow local temperature gradients. The hottest parts of the nucleus expel the most material. On the day side, the sun-facing hemisphere, you would expect strong outgassing. If the outgassing is concentrated in a jet rather than evenly distributed, and the jet happens to align along the comet-sun line, you get a sunward extension. Uncommon, but not impossible. Alternative interpretation. The object is performing a burn, a forward-facing engine designed to decelerate. If you perform a reverse burn to decelerate and enter a bound orbit, the engine exhaust will be directed forward in the direction of your motion. And depending on the rotation, the exhaust could be pointed toward the Sunday. Both explanations are consistent with the observations. The question is which is more plausible. Mass estimates are still debated. Loeb asserts that 3I Atlas has a greater mass than 1I, Oumuamua, or 2I divided by Borisov. Comet mass estimates are based on brightness, assumed albedo, and dynamical behavior. All depend on the model. If you assume the object is a mixture of porous ice and dust with a typical cometary albedo, you get one mass. If you assume it is denser, more compact, with a higher albedo, you get a different mass. If you include internal structure, like tanks or machinery, the mass increases further. Uncertainty is large. But if the object truly has a greater mass than expected, given its size and activity level, that is a data point that does not fully fit the standard comet model. After perihelion, the test becomes clear. Observers will track the position of 3I Atlas as it departs the Sunday. They will compare the observed trajectory with predictions based solely on gravity. Orbital mechanics is deterministic. If you know the position and velocity of the object and the gravitational forces acting on it, you can predict future trajectory with high accuracy. Any deviation from the prediction indicates an unmodeled force. For a comet, that force is usually outgassing. Asymmetric outgassing produces a small rocket effect. It is random, noisy, and usually minor. If 3I Atlas shows systematic deviations, velocity changes larger than predicted outgassing and in a specific direction, that is evidence for something else. If the deviation matches an Oberth burn, either accelerating to escape or decelerating into a bound orbit, the hypothesis gains weight. Observational limitations are significant. During the occultation, ground-based telescopes are blinded. Space assets, like SOHO and Stereo, might catch the object, but only in their wide-field images. SOHO's LASCO coronagraphs are designed to block the solar disk and image the corona. That is exactly the region 3I Atlas will pass through. Stereo has similar capabilities from other vantage points, but these instruments have limited resolution and sensitivity. They are optimized for bright comets with sunlight entering within a few solar radii. While 3I Atlas is at 1.4 AU farther out, it may be too faint to detect or too small to resolve. We will not know until the data is processed and released. That may take weeks. The timing is frustrating. If you want to witness the most critical moment, the potential Oberth burn, you cannot. The geometry does not allow it. The sun blocks the view. You are forced to wait. forced to trust that post-perihelion positional data will reveal what happened. Meanwhile, speculation runs wild, because there is no new data to constrain it. The occultation window is open. The object is at perihelion right now, or within a few days, depending on when you watch this. And here we sit in the dark, wondering what is happening 93 million miles behind the Sunday. NASA's official statements emphasize safety. No threat to Earth. Trajectory is well understood. The object will pass through and leave. No risk of impact. That message matters. The last thing anyone wants is public panic over a misunderstood visitor. But reassurance about safety does not answer the deeper question. Is this just a comet, or is it something else? And if it is something else, what does that mean for us? The next part of this story is about secrecy, about the possibility that high-resolution data exists but is not being released, about reasons, harmless or not, why information might be withheld. Because if there is one thing that accelerates conspiracy theories faster than vague data, it is the feeling that someone, somewhere, knows the truth but isn't saying it. Why is data withheld? Let's start with the mundane reasons. Reasons unrelated to secret government agencies or interstellar diplomacy. Reasons why scientific data might not yet be ready for the public, even when something interesting is happening. First, data quality. Not every observation is good enough to release. Astronomical images can be degraded by poor seeing, cloud cover, equipment glitches, calibration errors, or sheer bad luck. If you point a telescope at 3I Atlas and the atmosphere is turbulent, your image will be blurry. If the object is too faint, the signal-to-noise ratio will be terrible. If you miscalculate the pointing coordinates, you'll capture the wrong patch of sky. Professional astronomers handle this constant. They take many exposures, discard bad frames, and release only the good images. If an observatory obtains something ambiguous, it may look interesting, but is not scientifically robust. They might withhold it until confirmed by better data. That is not a cover-up. It is quality control. Second, calibration. Raw telescope data is messy. It includes instrument artifacts, dark, current, BS frames, flat field variations, hot pixels, and cosmic ray hits. Before analyzing a scientific target, all of that noise must be removed. Calibration can take days or weeks, depending on the complexity of the instrument and the skill of the team. If someone captures 3I Atlas during perihelion, but the data is still being processed through calibration pipelines, it will not be released. Patience is required. Science does not happen in real time. Third, proprietary time. Many observatories allow researchers to have exclusive telescope time. During that period, they have sole access to the data. It gives them time to analyze results, write a paper, and submit it to a journal before others can publish. Proprietary time can last months or even a year. This is standard practice to reward the effort of successfully writing an observation proposal. If someone has proprietary data on 3I Atlas, they are not obliged to release it immediately. Eventually, the data becomes public, but not right away. Fourth, spacecraft safety. If the data comes from space observatories like JWST or Hubble, operations teams prioritize the health of the spacecraft over any scientific goal. During solar conjunctions, some spacecraft enter safe mode to protect instruments from solar heating or to avoid dangerous pointing directions. Observing 3I Atlas during perihelion would require pointing dangerously close to the Sunday. The observatory will not do it. The risk of damaging expensive hardware far outweighs the scientific benefit. So the data you want may simply not exist. The observation is considered too risky. These are harmless reasons. They are normal, They are how science actually operates. They do not make an exciting story, but statistically, they are the most likely explanation for why high-resolution images of 3I-ATLAS at perihelion are not flooding the internet right now. Now, consider the less benign possibilities. Information is withheld, not for technical or procedural reasons, but because someone decides not to release it. National security. If 3I-ATLAS is determined to be artificial, that information would have strategic significance. It would confirm that interstellar travel is possible and that someone has already achieved it. It would raise questions of intent. Is this active or passive? Is it observing us or interacting with us? Is it alone or part of a larger fleet? These are questions that fall directly under defense and security. Governments may decide to delay releasing information to the public until there is a clearer understanding of what is happening and what the appropriate response should be. That is not necessarily malicious. It is risk management. When information is incomplete, caution is reasonable. Fear of public panic. History shows mixed reactions to astronomical discoveries. When Halley's Comet passed Earth in 1910, tabloid newspapers claimed the comet's tail contained poisonous gas that would kill everyone. The public panicked. Some sealed their homes. Some bought gas masks, all unfounded. The comet's tail was far too diffuse. It had no effect on Earth, but the panic was real. If 3I-ATLAS were announced as an object with potential artificial origin, but without conclusive evidence, the same type of hysteria could erupt. Governments and organizations may decide that preventing public panic is a valid reason to temporarily withhold ambiguous data. Again, this is not necessarily a literal cover-up. It is a decision about public communication. Verify before release. Imagine you are an astronomer. You capture an image of 3I-ATLAS that looks artificial. You are excited. You are also afraid of being wrong. If you publish and it turns out to be an artifact or a misinterpretation, your career suffers. You become the scientist who shouted aliens in the lab. Professional reputation matters in science. So you hold the data back. You show it to trusted colleagues. You request follow-up observations from other telescopes. You wait for confirmation, and while you wait, nothing is public. This is human nature, not malicious, just self-protection. Interagency politics. Space science is international. Many agencies, observatories, and research institutes are tracking 3I-ATLAS. NASA, ESA, JAXA, independent university teams. If one of them obtains extraordinary data, there will likely be negotiations over how and when to announce it, who gets credit, whose press release goes first, what the message will be. Those negotiations take time. They can slow public release even when no one intends to hide anything permanently. Bureaucracy and coordination are always slow. Now, regarding the claim that the leaked image originated from Japan, if that is true, if the clip really came from a Japanese source, what would that source look like? JAXA operates space missions, but currently, no mission is in a position to observe 3I-ATLAS at high resolution during perihelion. Japan's national observatories have ground-based telescopes. They can observe the sun and nearby regions. For example, Hida Observatory operates a solar telescope. University networks have smaller instruments. Any of these, in theory, could capture something. But if they did, and if it were important, you would expect an official announcement. The absence of any announcement suggests either the clip did not come from an official source or the source does not want to be identified. What would a genuine leak look like? In professional astronomy, data is stored in FITS format, a flexible image, Data Transmission System. It is the standard format. It contains both images and extensive metadata. Each FITS file has a header. It indicates the telescope, instrument, and filter, exposure time, observation date, and time down to the second, right ascension and declination of the field center, sensor temperature, sensitivity setting, observer name, program identification code. It is a forensic treasure. If someone leaked a FITS file, astronomers could verify authenticity within hours. They check whether the star field matches the claimed coordinates. They verify the point spread function against known optical characteristics of the telescope. They check whether the night's weather data supports the observational conditions. A real leak would be verifiable. What we have instead is a processed video. It has a watermark, no FITS header, no metadata, no way to trace it back to a specific device or observation. That is suspicious. It fits with a forgery. Someone made the clip and added a fake watermark to boost credibility, or a leak was deliberately cleaned. Someone stripped the metadata to protect the source. Both scenarios are possible. No scenario is ruled out. Commercial satellite data is another avenue. Private companies operate Earth observation satellites with very high-resolution cameras. Some satellites can be pointed toward targets close to the sun if the observation geometry allows, and if there is a customer request. Commercial data does not pass through public disclosure channels. It is not like academic data. If a private organization records something unusual, they may withhold it for commercial reasons, strategy, or contractual obligations. That creates data gaps. Non-traditional sources produce observations, but they never enter the public domain. That complicates provenance and makes verification harder. There is also the possibility of intelligence assets. Military and intelligence satellites have capabilities far beyond the public civilian tools. They are designed to observe Earth, but some are flexible enough to be tasked at other targets. If such an asset recorded 3I divided by Atlas during perihelion, that data would be classified. It would not be released through scientific channels. It might never be released. And if it were leaked, it would leak through the intelligence community, not through an astronomy forum. Watermark, anonymity, lack of metadata, all of that lines up more with an intelligence leak than with scientific disclosure. But here's the key point. Even if the data is withheld, even if there is a temporary delay due to quality control, interagency coordination, or national security review, that does not automatically imply aliens. Organizations delay releasing information for all sorts of reasons. The timing of the solar conjunction and the viral clip creates a perfect storm for cover-up narratives. But narrative is not evidence. The way to evaluate this is to watch what happens next. If post-perihelion data is released quickly, if multiple observatories publish results in peer-reviewed journals, if the orbit shows no anomalies, then the withheld data hypothesis collapses. Conversely, if months go by with no new data, if FOIA requests go unanswered, if observatories that should have observed the object claim they did not, or the data is corrupted, then the hypothesis gains weight. We will prioritize peer-reviewed sources and official agency statements for hard facts. When we speculate, we will label it clearly. That is the spirit of this video. We are not here to push a conclusion. We are here to map the terrain, to show where the data ends and speculation begins, so you can draw your own conclusions. But before we dismiss the natural object explanation outright, we need to take it seriously. Because there are scientists who have observed 3I Atlas, and they have not seen anything that requires an artificial origin. There are natural mechanisms that can explain the chemistry, morphology, and orbit. We owe the story a fair presentation of those mechanisms to show what it would take for this to be just a comet. A strange comet, but still a comet. Let's build the case for 3I Atlas as a natural object. Let's see how far we can go before the data forces us to admit we don't know. Start with the chemistry. Multiple spectroscopic observations have confirmed the presence of cyanide and atomic nickel in the coma. Cyanide is ordinary. It is one of the most commonly detected molecules in comets. It forms from carbon and nitrogen in the cold molecular clouds where comets are born. As a comet approaches the sun, ultraviolet light breaks apart larger molecules, releasing cyanide into the coma where it becomes detectable. Nothing unusual there. Nickel is less common, but not unheard of. Several comets have shown metal emissions: calcium, sodium, iron, nickel. These metals exist within rocky and metallic grains embedded in cometary ice. When the ice sublimates, it exposes these grains to sunlight. The grains heat up. At sufficiently high temperatures, the metals evaporate, releasing atoms into the coma. Those atoms absorb sunlight and emit at characteristic wavelengths, creating emission lines that spectrographs can detect. The puzzle is why nickel is prominent, while iron is weak or absent. In typical rocky material, iron is more abundant than nickel. The sun's composition reflects the overall composition of the solar nebula. In the sun, iron is about 20-to-1 more abundant than nickel. If 3I Atlas were simply outgassing ordinary rocky grains, you'd expect strong iron lines and weaker nickel lines. Instead, you see the opposite. That is unusual. The carbonyl chemistry explanation is quite elegant. Under certain conditions, nickel reacts with carbon monoxide to form nickel tetracarbonyl. This is a known industrial compound, a gas at room temperature, highly toxic and thermally unstable. When heated or exposed to ultraviolet radiation, it breaks apart, releasing nickel atoms and carbon monoxide. The key is that nickel forms carbonyl compounds far more readily than iron does. They require different environmental conditions. If the temperature and pressure in the near-surface layers of the nucleus fall within a specific range, nickel carbonyl can form. Then it photodissociates, pumping nickel atoms into the coma without a corresponding increase in iron. This process can naturally explain the nickel-to-iron ratio. Several peer-reviewed papers on 3I Atlas have discussed this mechanism. They model the thermal and chemical environment near the nucleus and show that carbonyl chemistry is plausible. It requires a carbon monoxide-rich environment, which JWST observations confirm. 3I Atlas is rich in CO2 and poor in water at large distances from the sunday. That is unusual for solar system comets, but not impossible for an interstellar object formed in a different stellar environment. Its chemistry, though strange, still has natural pathways. The sunward tail has a proposed thermodynamic explanation. When the sun-facing hemisphere heats up, it sublimates volatiles preferentially from that side. If the outgassing is strong enough, it creates a jet of gas and dust flowing off the surface. If that jet happens to align with the comet's sunline, it produces a feature that looks like a tail pointing toward the sunday. The jet is not actually moving toward the sun. It moves away from the nucleus. But because the nucleus lies between the sun and the observer, the jet appears to extend sunward. This is a geometric effect combined with active outgassing. It has been observed in other comets. It is rare but natural. High water ice would be typical, but interstellar comets can form in environments with less water ice. Different temperature structures in different protoplanetary disks lead to different volatile inventories. A comet formed in a system where CO2 or CO dominates over water ice would naturally show low water abundance. It is not standard, but well within the astrophysical possibility space. Diversity should be expected in a galaxy full of planetary systems with different formation histories. Now, the dynamics. The final exam for the spacecraft hypothesis is the orbit. If 3I Atlas's post-perihelion orbit matches predictions based solely on gravity, that is strong evidence it is a natural object. Non-gravitational forces from outgassing can create small deviations, but those deviations are usually random and small in magnitude. If the observed post-perihelion trajectory remains within gravitational error bounds, there is no need to invoke propulsion. The object is obeying Newton's laws. It is a comet. Outgassing torques can change a comet's rotation state and induce minor orbital perturbations. This is well documented. When gas jets erupt from the surface, they exert a force on the nucleus. If the jets are asymmetric, the force creates a torque that alters the rotation rate. If the jets have a net component, along or against the direction of travel, they change the orbit. These effects are small but measurable. Astronomers model them by tracking the comet over time and fitting a force model that includes both gravity and non-gravitational accelerations. For 3I Atlas, if non-gravitational acceleration is consistent in magnitude and direction with cometary outgassing, then the natural explanation remains plausible. Spectroscopy is another test. If the bright spots are real, they must behave like physical features tied to the object. They must rotate with the nucleus. They must maintain consistent brightness and color. They must appear in multiple filters. On the other hand, if they behave like point spread function artifacts, if they change with seeing conditions and vary between exposures without correlation to the object's rotation, that points to instrumental effects. High-cadence imaging across multiple nights can distinguish these cases. It is a falsifiable test. If the data show artifact-like behavior, the lights are not real. If the data show rotation-correlated behavior, they are real. And then the question becomes, what are they? Thermal physics provides another natural mechanism for the bright leading edge. Small dust grains scatter sunlight efficiently in the forward direction. If 3I Atlas has a dust coma concentrated sunward, and if grain sizes and viewing geometry are right, forward scattering could make that side much brighter than the rest of the coma. This depends on phase angle. The brightness should change as the phase angle changes. If observers track the object across different phase angles and see predictable brightness variations, that supports the scattering explanation. If the brightness remains constant regardless of phase angle, that contradicts scattering and supports intrinsic emission. History is full of comets that looked strange. Comet Linear fragmented in 2000, producing a chain of debris that appeared structured and geometric in some images. Comet Ison disintegrated at perihelion in 2013, creating razor-sharp dust features that looked artificial. Comet Shoemaker Levy 9 broke into pieces, looking like a string of pearls before slamming into Jupiter in 1994. In every case, the odd shapes had natural explanations. Fragmentation, Dedel forces, uneven sublimation, dust dynamics. Nature can produce forms and structures that look engineered if you don't understand the underlying physics. The burden is on us to distinguish what is design and what is merely unusual. The burden of proof for the spacecraft hypothesis is high. You would need to show non-gravitational acceleration that cannot be explained by outgassing. You would need resolved structure in multiple independent images, showing symmetry and regularity incompatible with natural processes. You would need spectral signatures that do not match known cometary chemistry. Ideally, you would want narrowband emissions at frequencies consistent with technology, radio carriers, lasers, microwave beams, something unmistakable. None of that has been officially reported. All we have is morphology and timing, suggestive but not conclusive. What would change a skeptic's mind? A recorded delta V, a change in velocity greater than outgassing, can produce and point it in a way consistent with intentional maneuvering. If 3 Atlas reappears after perihelion on a trajectory showing systematic deviations, changes in orbital energy or angular momentum, requiring forces that outgassing cannot supply, that is evidence. If the deviations point in the direction you'd expect from an Oberth burn, or an acceleration outbound, or a deceleration into a bound orbit, that is even stronger evidence. If multiple independent observers confirm the deviations and they cannot be explained by natural mechanisms, you are closing in on proof. Resolved structure from multiple instruments would also be persuasive. If Hubble, JWST, VLT, and Kiki all image it and show the same elongated morphology with covered nodes, and if those images cannot be explained by PSF artifacts or processing errors, you have to take it seriously. If the structure shows internal detail, features that look like joints, panels, antennas, emitters, things that have no business being on a comet, then the natural explanation collapses. Spectroscopy could be the decisive evidence. If someone detects emission lines that do not match any known cometary molecule or atomic transition, that is a red flag. If those lines are narrow, indicating a non-thermal source, that is a bigger red flag. If the lines are modulated, pulsed, or structured in a way that suggests information encoding, you've detected technology. But we are not there. Spectroscopy, so far, shows only CN and nickel, both with natural explanations. Skepticism is not cynicism. Skepticism is the scientific method. You start with the null hypothesis. This is a natural object. You collect data. You test whether the data is consistent with the null. If it is, you keep the null. If not, you revise. The natural object explanation for 3I Atlas is strained but unbroken. Its chemistry is unusual but explainable. Its morphology is strange but could be consistent with viewing geometry and processing artifacts. Its orbit is opportunistic but not impossible for a random interstellar visitor. We are in the gray zone. The data does not definitively prove a natural origin, but it also does not definitively prove an artificial one. The responsible position is to keep both possibilities open while demanding high-quality evidence before accepting extraordinary claims. We can enjoy the what-ifs, explore the implications, but we cannot let speculation override the need for accuracy. And right now, the data quality is not enough. We are working with leaks, anonymous clips, amateur imagery, incomplete spectroscopy. It is intriguing, but not enough. If 3I Atlas is a probe from another civilization, we are not alone. Not being alone changes everything. For the sake of this section, suppose 3I Atlas is artificial, a probe, a spacecraft built by an intelligence that is not human, launched from a star system that is not ours, sent with a purpose we can only guess at. What would that mean for us? The best case scenario, it is a reconnaissance mission, a fully autonomous robotic explorer, surveying the solar system. It collects data, it maps planets, it measures the sun's output, it samples the composition of asteroids and comets. It checks for biosignatures on Earth, Mars, perhaps Europa, or Enceladus. It does science, the same kind of science we try to do with missions to other worlds. In this scenario, the probe is passive. It observes but does not interact. It does not come for contact. It comes to gather information and report back. or perhaps to add our system to a growing catalog of surveyed stars. This is the optimistic view. First contact is mutual curiosity. Civilizations explore the galaxy and eventually find one another because we are all curious about what is out there. In this scenario, an Oberth maneuver around the sun makes sense. As a mission design choice, you enter the system on a hyperbolic trajectory. You swoop close to inner planets to maximize observation time. Then use the sun's gravity well to slingshot outward. Maybe you head for the next star on the list. Maybe you return home with memory full of data. Either way, you are using the most efficient propulsion strategy possible for a fuel-limited craft. You are doing it smartly. Economically, that is what we would do. That is what any reasonable spacefaring civilization would do. The implications of this scenario are profound, but not immediately threatening. It means interstellar travel is possible. It means someone has done it before us. It means the galaxy is not empty. There are others out there building machines, exploring, learning. It means we are part of something larger, a wider community, even if we have never met. It shifts the entire context of human existence. We are no longer special. We are no longer alone. Our achievements, our struggles, our history, all have taken place in a universe where intelligence and technology did not begin on Earth and do not end here. That is humbling. If 3I Atlas is truly a comet, then it is a reminder that the universe still holds things we do not understand. If it is a probe, then it is a greeting from someone who has traveled farther than we can imagine. Comet or spacecraft, the story carries the same weight because it forces us to look inward. We, humanity, are still learning how to listen, how to separate noise from signal, what we fear from what actually exists out there. Evidence is the only light we carry through the long night of the cosmos. And sometimes, that light is so faint that all we have left is faith in reason. Maybe 3I Atlas is just a wandering shard of ice, cast out from its birthplace millions of years ago, crossing the cold dark, passing through our solar system by chance. Or maybe it is a message, a guide d'observation from a mind farther than we can conceive. In the end, the answer is not what matters most. What matters is how we choose to ask the question. Science does not promise certainty. It only promises that we will keep searching. Every time we look up at the sky, every point of light reminds us that we have only begun to understand this world. If someone out there is listening, I hope they are as curious as we are. I hope they want to know who we are and why we keep looking up. And if no one is there at all, then it is our curiosity that makes us different, not because we are alone, but because we keep asking, even when no one answers.